Howdy, my name is Joydeep and this is the third presentation in the MSCN 660 Materials Informatics presentation series. Today, I will give a brief presentation on the paper titled Deep Learning for Automated Phase Segmentation in EBSD Maps, a case study in dual-phase steel microstructures. This paper has been published in 2021 in the Materials Characterization journal, and so far, till date, it has acquired approximately 40 citations. This paper has been published from University of Lorraine in France, and the experimental collaboration has been conducted with ArcelorMittal R&D, where the specific dual-phase steel samples has been obtained after post-processing heat treatments for experimentations. To begin, the motivation behind this paper is to eliminate the need of human labor for conducting EBSD post-processing analysis for the phase identification. The issue with conventional EBSD phase analysis is it is extremely subjective to the user. There is bias, inconsistency, variability in terms of users, and as well as it is extremely time consuming. The main goal, the idea behind this research is to basically accelerate the phase segmentation as well as minimize the subjectivity and manual effort to identify complicated microstructures, particularly for multi-phase materials consisting of multiple phases within the same microstructure under inspection. So the main goal is to automate this entire process from the electron backscatter diffraction maps and train certain models based on deep learning to generate these complicated microstructures with better accuracy, robustness, so that they can be implemented for real-world applications and image analysis. Here on the right, you can see a specific snippet that gives the basic summary of what this paper is about. As I reiterated before, the conventional route is to segment the EBSD images and analyze the phases manually using post-processing softwares, which is conducted by humans. In this study, there's a unit-based convolutional neural network deep learning architecture that selectively identifies and differentiates the phases from the EBSD raw data, and the accuracy is much better than done manually. It is approximately 2% better than the conventional method. Here is a brief experimentation and computational workflow for the paper. Basically, the material was first acquired and as a DP steel, which comprises of a dual phase microstructure comprising of ferrite and martensite. And this data acquisition was conducted in multiple orientations. A lot of images were taken in different quality indices. Then the images were labeled using, they were pre-labeled using a trainable Weka segmentation, and then the refinement was conducted using orientation analysis as well as semi-automatic grain detection. The UNet model was then deployed for semantic segmentation, and the inputs for those models were different EBSD maps and parameters like band contrast, band slope, kernel average misorientation, and raw orientation data as the inputs. Then the data augmentation was conducted in the training data set with different downscaling techniques as well as rotation. The model was also checked and tested for robustness and whether there was any variation in the resolutions of the maps. Then the unit was trained in various EBSD frames, and the training and the validation data was split in an 80-20 ratio. The model was tested and different parameters were analyzed. The inputs, more or less the band contrast, band slope, and the kernel average misorientation, they were able to obtain a high classification accuracy, approximately more than 98%. And when compared to other algorithms, the unit was performed much better. The data was also optimized in terms of sensitivity analysis, in terms of input sizes, the training set composition, as well as the network depth, as well as finally the robustness check was conducted. If there was any error in labeling or there was any variations in the input data, it was checked to increase the efficiency of the model. So initially, we go into the experimental part where the dual phase steel with a mixed ferritic martensitic microstructure was processed using different heat treatments. The main idea was conducting 3 different heat treatments to basically optimize the proportion of the martensite phase. So as you can see from the left to the right of this microstructure, the martensite phase actually is more prevalent than the ferrite. So the phase fraction increases. So the EBSD maps were used as indicators to distinguish the ferrite from the martensite, and each indicator had this specific property like map, like these parameters were inputted in the machine learning model, like band contrast. Band contrast is basically gives the diffraction pattern quality. The band slope highlights the intensity of the gradients in the EBSD patterns. Kernel average misorientation is used to identify the dislocation density, and quaternions is basically to understand the raw orientation data that basically describes the different crystallographic orientations of the specific microstructure. And then labeling was conducted using the trainable Weka segmentation. The idea behind the refinement was to utilize a semi-automatic grain detection and orientation analysis, and each individualized pixels were like corrected to improve the efficiency and accuracy of the classification. And then the ground truth labeling was conducted in the ferrite and martensite, which was used as a benchmark to model those training and evaluation data. And if you look at the figure on the right, these specific EBSD indicators from the left to the right are the band contrast, the band slope, the kernel average misorientations, as well as the ground truth data. Each indicator except the ground truth are basically has their own histograms. Now, the deep learning architecture was implemented, but before that, the data augmentation was conducted. If we look at the figure on the right, data augmentation was applied to the band contrast image of the particular EBSD map, and it provides additional 11 maps from the original one that are stitched together. The original map is highlighted in the red just for reference. And then on the right, we have the sliding window without overlapping. It is used in all channels to obtain the training and the validation crops. And then like after data augmentation, the maps were specifically like clustered or segmented in training and validation sets in an 80-20 ratio, and then it was used to train the UNet CNN model to evaluate the performance on the already acquired data as well as the unseen data. Now, the UNet architecture is basically used convolutional neural network model that was used for the semantic segmentation, and it is chosen because it has its proven capability to identify and classify images based on pixel-wise wide classifications. So different types of input parameters like band contrast, band slope, kernel average misorientation, and quaternions were used to handle those multi-channel inputs. The main architecture of this UNet program was the U shape with like a contracting path. As you can see, it goes down with the classical convolutional neural network steps like convolution, then activation and downscaling, and then there's like a symmetric expansive path which comprises of the convolution, activation, and upscaling. And additionally, there are various skip connections are present that enable the combination of high resolution features from the contracting path with expansive path to actually improve the resolution of the unsampled outputs. And finally, after the model is tested and like trained and tested in the UNet architecture, it was obtained that the model they were able to obtain 98 greater than 98% accuracy in features that comprise of kernel average misorientation, band slope, band contrast. Quaternion based models performed relatively inferiorly, showing 95%, but they are still better than the user defined post-processing, which shows its potential to handle the raw orientation data. The models were then generalized and new datasets were utilized, and the labeling errors were actually removed. On the top image, you can see this is a band slope image, and then it also has a ground truth. The accuracy maps are present in the individual band slope, kernel average misorientation. And on the far right, you can see the accuracy actually improves if we couple both the band slope and the kernel average misorientation models together. So essentially, it improves the efficiency of the model. It goes up to 99%. And this is on the specific heat-treated dual-phase microstructure. And then in the second image, there is the band slope and the ground truth of like a random microstructure that does not belong to this original data set, and it's still the combination of the band slope and the kernel average misorientation shows greater than 95% accuracy. And if you look at the figure on the bottom, it shows the training. This basically plot represents the training and the validation classification accuracy against the number of epochs for all the 4 models that are tested during the entire machine learning process. The high classification accuracy was achieved above 90% in the initial stages of the training process. After 15 epochs, you can see the training and the validation classification accuracy of the band contrast, band slope, and kernel average misorientation, they tend to converge with each other. And at 25 epochs, the training classification accuracy of the quaternions showed an upward trend, while the validation remained fairly constant. So this indicates overfitting. So this is the reason why the model has been trained until 25 epoch, and it was selected to be the final threshold. And approximately it took 700 seconds for each epoch to complete, and it resulted in higher accuracy. So the take-home message from this paper is the basic contribution to the material science is, number one, it's automated. So using this UNet framework or architecture, uh, we are able to segregate and differentiate phases with much better accuracy, and it does not require any human labor. It is also much efficient, and it is thus it is able to rely less on like human, and there is expert intervention is not required, as well as pre and post processing, and it is scalable. So the idea behind this is that this can be applied to a wide range of microstructures uh, comprising of multi-phase and complicated like phases, and it is able to segregate and differentiate, as well as identify those individual volume fractions as well of those phases within the specific complicated microstructure and larger data set at an accuracy which is much higher than done manually. Thank you.